recording. Okay, so we'll probably won't finish all the two sections we're going to try to cover today on conductivity and resistivity, which is related to current, which is what we just learned about earlier this week. But hopefully I'll be able to wrap this up tomorrow and do another little activities with current, okay, tomorrow before the week ends. Okay, so remember the picture I want you guys to have when you think about current, meaning electron current or just regular current, is that inside a conductor, right, there's all these nuclei around, right? Right, conductors are made of atoms, and atoms have a nuclei and a cloud of electron around it, right? The idea is that these electrons, doesn't get to go in a straight line. They're kind of bouncing back and forth, in this little they call it a lattice of atoms inside your conductor, right? But what happens is that if you apply an electric field to it, let's do that in orange, okay? If you apply an electric field on that conductor, what happens is that then the electrons, instead of going around bouncing off like this, right, they will tend to drift towards the other end of the conductor, right? Right, and the reason that the electric field is going to the left and the electrons are going to the right is because, right, basically imagine electrons as kind of flowing uphill, along a stream of electric field, okay? And we can quantify this, right, with, first we derive this equation for the current, which is the number density, meaning how many electrons are available to be bouncing around in the first place in our material per meters cube, right, times the charge of the electron, times the drift velocity of that electron, times the cross-sectional area, right? So we want to picture this as kind of like the cross-sectional area, okay? But then, right, as we do in physics, having one equation is not good enough. Let's make like 5 or 6, right? So we decided that, well, let's divide both sides by A, right? And that gets us to this equation called current density, right? Current density is how much current is passing through that wire per square meter, okay, in SI units, okay? How much current is there per square meters? The reason for that is that it kind of removes the geometry of the wire. So if you know that the current density, let's say it's like a 1,000,000 amps per square meter, right? If you double the cross-sectional area of that wire, you basically double the amount of total current, right? So it's just a way to quantify the amount of current that can pass through your conductor, without the conductor melting or something like that, by kind of dividing out this geometric, right, physical geometrics, how thick the wire is, right, and that's quantified by this area. Okay. Now what we're going to do is combine this with something we learned from, I think, on Monday, right, where, right, the bigger this electric field, right, the bigger the drift velocity, right, the faster it'll drift to the other side, okay? And we calculated this, I think, on Monday, where the drift velocity is the charge of the electron. And remember, this tau is the mean the mean free path time, meaning it's the amount of time the electrons are actually kind of is between the two different nuclei, so they're actually being able to be accelerated by the electric field, okay? And of course, since we're dealing with velocity, it's going to be inversely proportional to mass, right? The heavier stuff goes slower, the less massive stuff will go faster, okay? And this is, of course, proportional to electric field, as we stated, right? It makes sense for the bigger the electric field, the faster the electron will drift across our conductor, okay? Now we're going to combine these two equations because we see that there's a drift velocity thing in here, right? And this is kind of like a little equation how we're going through, but on the other end it's actually better, okay? So we'll see how this will actually make things better at the end, okay? Combining these two equations together, right, we end up with this complicated, crazy equation, right, for current density, right? It's still proportional to the electric field, right? So hopefully it makes sense, right? The bigger the electric field, the more current you get, right? Hopefully that makes sense, right? There's these complicated pieces to it, right? The electron number density on your material, the charge of the electron square now, right? Because we got one factor from here and one factor from here, right? So we get a square version of that, and we still have this mean free path time, right, tau, in our equation, okay? Okay, so what's the point of all of this, okay? So, right, what we're going to do is we're going to lump, go back down, lump all of this stuff, these complicated stuff, into a single number. Why can we do that, right? So the electron density, right, if you have copper, it'll have a number to it. It's like 8.5 times 10 to 28. If you have gold, it'll have one number. If it's, let's say a bad conductor like silicon or something like that, it'll have a particular number, right? So this depends on the material, right? Right. So whatever material we're dealing with, okay? Well, the charge of an electron, is always the same number, all right, unless you go to a different universe, okay? The mean free path time, this also depends on the material. The denser the material, the shorter that time, right? The less dense that material, the longer that amount of time is, okay? And mass of the electron, of course, is just the mass of an electron, which is always the same in the current universe. What we're going to do, right, all of this number, okay, just depends on what type of material it is, right? We're going to lump all those numbers together and call it conductivity, right? How conductive is my piece of metal, okay? So we're going to define this thing called sigma, right? This is the Greek letter sigma, okay? We're going to call that conductivity. And it's just going to be, all that stuff, all that complicated stuff, that's in our equation, okay? So in that case, right, that's why on the other end, you end up with a very simple equation, right? The current density is just the conductivity times the electric field, right? That's nice. 3 variables I can always deal with, right? It's like 6 or 7, that's when things get a little bit hairy, right? And the conductivity for different materials are given to you in a table in the textbook. You can also look it up on the internet, of course. So the conductivity, we're going to introduce this new unit called ohm, and we're going to describe what that is at the end of the lecture, unfortunately. So just for now, just trust me that it is a SI unit, okay? So when you're using all SI units, those ohms are going to be canceled out correctly, okay? So you don't have to actually carry it around. Okay, so for example, the conductivity for, where's copper, right? For copper is 6 times 10 to the 7, right? Gold is also another good conductor, right? Aluminum is not as good. Carbon, right? So basically the conductivity, if you have wood, for example, that's made of mostly carbon, right? The conductivity of carbon, actually probably not wood, like if you have a sheet of graphite, that's probably what will be closest to carbon. It's much lower because it is a bad conductor, right? It's still conductive, but it's not, it's like a factor of 1,000 worse than gold and copper, right? So with the same electric field, you will have a current that's 1,000 times less if you try to conduct electricity through a graphite, which is basically like the lead of your pencil instead of a piece of metal. Okay. One more backflip. It's often actually easier to work with a different quantity than conductivity, and this is going to be called resistivity. Okay. Resistivity is just the inverse of conductivity. Okay, it's just 1 over conductivity. Okay, and we're going to see why resistivity is just going to turn into this thing called Ohm's law, which is the goal of this chapter. Right? Resistivity. So if you just take this number, take the inverse of it, you will get the If you take the inverse of conductivity, you get resistivity. Okay, so one versus the other. There's a 1-to-1 correlation. This is resistivity is not a new thing, right? But conductivity is the new thing, and they're both related to each other. Okay. Okay. And if you want to calculate resistivity of something, right, it's just the reciprocal of conductivity, right? You just take this and you flip it upside down, and you'll have resistivity instead. Okay. So the equation for our current density with resistivity, right, it's just going to be E, the electric field strength, divided by the resistivity, which is using this. We're reusing this Greek letter once again, right? This is the Greek letter rho, right? We use it for density, but we also use it for resistivity, so be a little careful about that. Okay, so we'll deal with the SI unitness of it when we get to Ohm's law and see how those cancel out. But for now, let's just do an example calculation, right? So we can find the electric field in a wire, right? If we're given, the diameter of the wire, the material is made of, right? So it's often important to notice what material the stuff is made of. Okay, the amount of current. Okay, and we want to find the electric field strength inside this wire. Okay, so in the setup of the problem, right, I'm going to draw the little copper wire as just kind of a cylinder, just so I can have a picture of what's going on, right? And I expect, if we're going to have a current going this way, a regular current going this way, which way should I draw the electric field? This is a tricky one. Should I draw the electric field to the left or to the right? The regular current. How many think I should be drawing it to the right? There's one. Okay. How many think we should be drawing it to the left? Okay. All right. So I'm being tricky on you. Right? Remember the original picture, the thing we want to think about? Let's go all the way up here. Right? Electrons, right, go in the opposite direction of the electric field. What is current? I'm sorry? Right, current is the electron current times the charge of an electron. And the charge of an electron is negative 1.6 times 10 to the negative 19 coulomb. So therefore, electron current and current always goes in the opposite direction of each other. Okay? So, and this is, the problem, and I always blame Benjamin Franklin for this. When he started studying electricity, he and other people around him, it's not only his fault, right? Assume that it's actually positive charges that moves around in the conductor. Okay? So therefore, all the convention assumes that, okay, that current has a positive charge on it. Even though none of those positive charge nuclei are moving around, right? It's only the electrons that's moving around. So don't get confused by this, okay? So when you're dealing with regular current, it's positive charge moving around. If you're thinking about pushing positive charges around, right, then the electric field will have to be in the same direction as the current, okay? In fact, I think it's probably better to draw it this way, where you have a bunch of E fields, right? Right, that's inside here, okay? So if it's confusing, it's not meant to be, it is confusing because of the situation back in the 1700s, okay? So that's your historical artifact, okay? Okay, so now that we kind of have a picture of what's going on with the current, right? So this, little wire has some cross-sectional area, right? This area is just going to be pi times r squared, right? And r in this case, right, is just going to be 1.0 times 10 to the negative 3. I'm going to do everything in meters, right? Because that's the SI units we're going to have to deal with eventually. Okay, if we calculate that, then we get 3.14 times 10 to the negative 6 meters squared. Okay. All right, so far so good. So that gets us to the area. We want to figure out what the, oh, do we actually not care about the area? Oh, we do. Okay, so the wire carries 800 milliamps of current. Okay, so which letter is this associated with? Is this J or I? Which one do you think? It's I, right? Because so one way to notice it is that, remember, J is amps per meter square, and I is just regular amps. Okay, so since they gave you the units of amps, therefore, right, it's just actually current. But what we actually need for the problem in our equation is actually J. So let's calculate what J is. So this is more of the solving part. Right, J is actually the current divided by the area. So this is 800 milliamp. So 800 times 10 to the negative 3 amps divided by 3.14 times 10 to the negative 6 meters squared. And this is where a calculator is useful. Right. Unlock my phone. 800 e to the negative 3 divided by 3.14 10 to the negative 6. Then you get 2.55 times 10 to the 5, and this will have amps per meter square. Okay. Okay. The goal is to get to the electric field. Okay. Right. So instead of plugging in all these crazy factor here, right, what I can do is just look up the conductivity of aluminum or the resistivity of aluminum and apply that equation. What I'm going to do is I'm going to do the resistivity because we're going to use resistivity after this. Right, so the electric field is actually just the current times the resistivity of aluminum. Okay, so aluminum's resistivity is up here, which is this first column, which is this number, 2.8 times 10 to the negative 8. That's a positive amps per meter squared. And this is going to be 2.8 times 10 to the, what did I say, negative 8? And this has units of ohms per meter, I think. Ohms meter. Okay. Okay. I'm going to deal with the units in a bit, but all of this is going to be in SI units. So what will be the units at the result here? What's the units for electric field? There's two of them that you can use pretty easily. Newtons per coulomb or volts per meter. Okay, either one is fine. Okay. Okay. 2.8 e negative 8. Okay. So the electric field is 7.1 times 10 to the negative 3. Okay. So electric fields inside conductors tends to be very small, right? Because, right, the charges are actually kind of moving around in order for it to reduce the electric field. Okay. So let's do a little. Yeah, lady. Right, on an exam, you'll always be given those information. You don't have to memorize them, but kind of know what they are, like, you know, big number versus small number, right? Okay, okay, okay. Now we have the little diversion. This is not going to be on a homework or exam or anything like that. So if you guys want to just stop paying attention, you can if you wanted to. But this is, to me, like a very interesting thing, where this is something I actually studied when I was a student like you guys. It says superconductivity. How many of you guys heard of superconductivity at some point? You know, a little bit, right? Superconductivity, the idea of superconductivity is that you want to make a material that basically either has infinite conductivity or zero resistivity, right? So how can we do that, right? Because the problem is that, right, when you have your electron, moving around inside your conductor, they're bouncing around all these atoms, right? Right? How can I make is it possible for me to make the electrons so it actually does not bounce off these atoms at all? Right? Is that even possible? You have all these, if I want to run through this room without hitting any of you guys, right? How can I do that? Right? Because I'm going to be bouncing off of you guys, right? So what happened is that, and this is something that's beyond what we need to cover, what we cover in this class. This is actually, superconductivity is actually a quantum mechanical effect, where what happens is that you have to cool the material enough, and this is kind of like opposite of what you think should happen, right? If you cool a material, right, things seems to move slower, not faster, right? Okay. And the reason you want things to move slower is because you want the electrons to actually move slower through the material, right? It's very, very counterintuitive, right? Because you want more electrons to get through the material, but you want them to move slower. That doesn't make any sense, right? But what happens is that when the electrons are moving slower, and this is another view of the, these positive nuclei, in our material, okay? And this is drawn in a way so that it's actually a very ordered material. So only certain material can be superconductor, not everything can be, okay? And what happens is that once the electrons start moving slower, okay, the first electron that's passing through is actually, it's going to warp, right? Because when the electron is here, right, these positive charges are going to be attracted to that electron, right? So it actually kind of makes a little divot here, right? What happened there is that it actually creates a little bit of a zone of extra positive charge, okay? It's a little bit too more positive here. And what happened is that the next electron basically kind of follows that, okay? Okay? And what happened is then, while this keeps happening, so you basically kind of creates a little tunnel for the electron to pass through straight versus bouncing off the lattices. Does that make sense? I mean, I'm not quantifying it, but hopefully the conceptual view makes sense, right? So instead of me running really fast around this room bouncing off of you guys, if all of us just kind of file one by one through the middle here, right, we're not going to have a lot of resistance, right? That's the idea of superconductivity. And hopefully that makes sense, okay? In order for a material to be superconductive, as I said, it has to be kind of an orderly process, right? You have to slow down the electrons, okay? So for example, if your material is made of aluminum, you have to cool the material down to 1.2 Kelvin. So that's negative 271.8 degrees Celsius. I don't know what it is in Fahrenheit, okay? So it has to be super cold in order for that to happen. Current research is trying to increase this number so that you can actually, the ideal goal is actually to have room temperature superconductor. Can you guys think of anything that can be useful if we have room temperature superconductor?
Battery.
I'm sorry?
Battery.
Battery, that stores electrical energy, right? What's one of the things that, let's say we have a bunch of solar panels here, right? But then, someone in Minnesota wants to use that power. What would we have to do? We have to connect it through a wire, right? And those wires, right, when they're not superconductive, has resistance to it. So you're going to lose like, maybe 80 or 90% of the energy by the time it gets to Minnesota, right? But if you have superconductor, you will lose none of that energy, okay? And so, we'll see how this turns out. Maybe before, by the time you guys are, doing research in this stuff, you may be able to make the next room temperature superconductor, and this is a extremely well-funded part of research in physics to figure out how do we make conductor that are superconductive at room temperature, right, in order to transmit energy so that we don't lose most of it by just sending it back and forth, okay? It's also useful in electronics, right, where if you have room temperature superconductor, the cool thing about superconductor is, the thing about superconductor, I didn't want to say cool, is that you're not gonna create heat in your system. Those of you who have laptops and stuff like that, right? There's a little fan here, and that's because the regular conductor in there, right? What happens is that it's going to dissipate heat as you run the system. But if you have superconductor, then you don't have to dissipate heat, then you don't have to have all these fans and stuff like that. It'll save you on your battery life. Okay. I'm sorry.
Wouldn't that make like heating essentially free?
Well, you still need to set up the initial states of all the bits and stuff like that. So you have to, ramp up voltage, ramp down voltage. But like, yeah, the process inside the computer will be kind of like energy free, right?
Yeah.
Yeah, which is kind of nice. Yeah. Yeah. Okay. So one thing I want to show you guys about superconductivity when you look at it on the internet, there's all this stuff about the Meissner effect. Okay. If you have a superconductor, a lot of misconception about it, so if you look it up on the internet, is that if this blue ball was a regular conductor, meaning just metal, right? Magnetic field, I know we didn't talk about magnetic field yet, but the book brought it up here, so that's why. The magnetic field can penetrate through the conductor, right? Okay. And what a lot of people taught when they say talk about superconductor, is that the magnetic field, if this material is superconducting, right, the magnetic field goes around it. Okay, it's like a magnetic shield. Okay, people think about, oh, you can use superconductor as a shield for electric field or magnetic field if someone's pointing a laser at you or something like that. Okay, this is actually a slight misconception. The drawing is almost correct, but I just want to point this out. Okay, where let's say you have a superconductor like this, what happens in reality is that the magnetic field will still basically technically penetrate through the superconductor. But what happens is that the superconductor have these electrons inside it, and they're going to move in a way to create a magnetic field that is equal and opposite to it. Okay? It's a magnetic field canceling effect, not a shielding effect, if that makes it. Sorry for being so pedantic, but this annoys me all the time when people show like YouTube video. Oh, you have superconductor that can shield you from magnetic fields. Like, no. In essence, it does, but the technicality is that it's creating a material that actually gives you exactly the equal and opposite magnetic field inside the material. Okay. Since I only have 3 minutes, let's not try to rush through the next section, which is the last section we'll cover, but we can watch this little video while you guys pack up and get ready to head out, which is on a little demonstration of superconductivity, and since none of this is going to be on your test or anything like that, but it's just a little cool little video. Fast forward through it. Okay, where you can levitate a magnet